Good afternoon. I think we have it set correctly. What we have learned so far is two methods for risk assessment. One that depends on the concept of creating the equivalent of a Richter scale, what we call incidence and likelihood risk indices. It's a very simple method. This is a method that we invented here. I think there is a paper published in the conference part of the portal of the course. However, we started also learning a second method that depends on the field of economics. So it doesn't need really much of a complicated background. This is the method of marginal, thank you, cost-benefit analysis. And we started looking at that last time. We generated the graph that shows us the risk for any inherent technology or social activity as a function of the cost of risk reduction. And we suggested that any technology, any procedure that we use in our society, human life in general, has an inherent risk. We can reduce the risk by large amounts by spending initially a very small amount of time. And I gave you a problem as an example that you could figure out yourself, adding a higher level of safety, decreasing the risk of car accidents by spending $200 here, delta C1, for maybe a seat belt. We suggested that beyond that, you'll find that you can spend more money to reduce the risk further, say for, let's say, anti-lock brakes, $800. This is an example that you have to work on as an assignment, but you spend more, like say you spend $800. If you want to reduce the risk even further, yeah, you can add the airbags for the driver, airbag for the passengers, back kind of videos, radars to stop you from hitting the car in front of you. But every time you add one of those features, you are able to reduce the risk a smaller amount, but by spending a large amount of money. So that's in economics called the law of diminishing return. So it depends on the economics there. We suggested that from that perspective, the risk can never be reduced to zero, meaning that you cannot claim by adding all the safety features that you can think of in a given design or even in economics or in a social procedure, any activity, you cannot reduce the risk to zero. There is nothing like absolutely safe risk. Now came people in Germany and they became very sophisticated and they suggested the following. They suggested, but when you manufacture that seat belt, or you manufacture the anti-lock brakes, or you manufacture all those cameras and the radars and so on, this is a human activity that involves some risk. You have to manufacture, say, the threads in the seat belt or the integrated circuits for the radar and the cameras and so on. And every human activity involves some risk. The least of it is, of course, driving just to work. There is a risk in driving back and forth from work. So they suggested that, well, we have to think when we reduce the risk that there is an overall economical system at play. And that when we add more safety features, in fact, we are adding some level of risk. But the risk does not decrease here like exponentially. The risk in that case, in adding the different safety features, increases in a linear fashion. So in that case, I came up with the idea that we should consider the overall economic system when we consider the level of risk. And this approach is very wonderful because it tells us, okay, as we invest in money to decrease the risk, we are adding a little bit here to the level of risk. So in that case, what do we get? We get a monotonically decreasing kind of curve. That's in mathematics what we call that decreasing curve, but the investment is introducing a risk. Think about manufacturing the anti-lock brakes. You have to produce steel, you have to mine for coal to melt the steel. So you add some, or if you have a nuclear power station, you add diesel generators for the cooling of the reactor core when it's shut down. You'll find that you add some investment, and luckily it's a linear investment. Now we have a monotonically decreasing graph here and the monotonically increasing linear curve in the investment. So what is the total risk as a function of the cost of risk reduction? You find that it decreases, slightly larger here because there is an increasing risk. But at some point, the draftman did not do a good job here. You always reach a minimum. Do you see that? A decreasing function monotonically, an increasing function monotonically. When you add them, you decrease a minimum. Beyond that minimum, it doesn't make sense to start adding more investment. So instead of depending on the Nuclear Regulatory Commission telling us, oh, if the cost of risk reduction decreases the dose rate by a certain amount, then you implement the safety feature. In that case, beyond that minimum, it doesn't make sense to keep adding extra safety features. So this is a system that depends now on the overall system. It is much more difficult to implement because you'll have to go and think about all the components of the system and how it decreases the risk. All right, so we have two approaches really to risk reduction. The simple approach here that is described in terms of the cost-benefit ratio. And the cost-benefit ratio is basically the annualized cost of adding a given safety feature, say the emergency core cooling systems per year for a nuclear reactor. I take the example here because that's where this idea or that technique has been first applied. That's $1.5 million per year. And in the denominator, we subtract the risk before the addition of the safety feature. Here is our equation here for different options minus the risk after we implement the safety feature. We applied it for a nuclear power plant, and you'll find that to add that emergency core cooling system, that's the acronym for an emergency core cooling system, benefit to cost-benefit ratio is that you spend $14 per reduction of the dose rate as a result of a possible accident of one person getting 1 rem of radiation. And here I have to stop and describe to you, for those who haven't studied nuclear engineering, what am I talking about when we talk about the rem? The rem has to do with the level of radiation that we get, of damage basically that we get from being exposed to radiation. And the way we measure it is by using what we call the rad. So 1 rad, take a note here because I don't have that in the notes. 1 rad is the radiation absorbed dose. All right, so that's the abbreviation for the rad. And this is in the CGS, or the conventional system of units, a centigrade, centimeter, gram, and second method. Now, in the SI system of unit, which is a new system of units that we use as engineers and scientists, the unit in that case is called the gray. And gray was a gentleman who worked in that field, and it's abbreviated as 1 gray. And you'll find that 1 rad is the amount of energy absorbed by living material, whether it's plant material or human body, not the human, any living material, animal or plant. And it is equivalent to the absorption of 100 ergs. Ergs is the unit of energy in the SI system of units per gram of any material, any material. All right. So in that case, one rad, we can say, is equal to 1 centigrade. All right. Now, that does not account for the fact that different types of radiation can cause different levels of harm. So when we want to consider the different types of radiations and the different types of harm, we define another unit that we call the REM. The REM stands for radiation equivalent for E, man. And you could see here, one REM is one radiation equivalent man, and it is equal to the rad value here multiplied by a factor that we call the basically the quality factor. The quality factor depends on different types of radiation, and the reference is the 100 kilo electron volt X-rays. So if you are subjected to 100 kilovolt X-rays as humans, you'll find that that Q is equal to 1. But if you are subjected to other sources of radiation like alpha particles or neutrons, that can become up to 20 for heavy ions in that case. So the REM is the Q multiplied into the rad, and the unit in the SI system is what we call the sievert. And you read about that sievert quite a bit when you read about the Fukushima accident in particular, because they have all their measurements in millisievert or sievert. Millisievert means 1,000th of a sievert. And the way to remember the relationship is the same, that one REM is equivalent to 1 centisievert or 100th of a sievert. So here, if you haven't seen that before, the rad is a unit of absorbed energy that can cause damage. How does it cause damage in living matter? That living matter is composed of a cell. Inside the cell, you have a nucleus. And in the nucleus itself, we have those chromosomes, and each one of those chromosomes have as nodes on it the genes that determine, of course, all the functions in our body. And if radiation comes in, let me show here a gamma photon, it can cause many different effects. It can break those chains here, or it can get a gene lost out. So in that case, it breaks those chromosomes, and then that cell now starts dividing in ways that were not expected before. If they divide in a way that is beneficial to the individual, oh, you gain immunity and you become a new basically strain of any plant or animal that applies to animals too and plants. And just watch how many different strains of dogs we have. Every strain would have a different type of genes, and we basically have no control on it. We are, each one of us is being dealt a deck of cards when we are born with our genes. We have no control on it. So in that case, the amount of energy absorbed determines the damage that can happen to the genes on the chromosomes in the nucleus of the cell in that case. So that is why when we talk here about the, I lost the cover. When we talk about the dose reduction, we multiply the number of people that received 1 REM of radiation, which represents the damage, say, from a leakage of radiation from a nuclear power plant. Or you can think about the bacteria that are spread from the COVID-19, whatever kind of risk that we are facing in society in general. So you could see here that $14 per person REM. Now, without the idea of dealing with the overall economic system, adding that emergency core cooling system, and that is an actual case from the reactor safety study that studied the safety of nuclear power plants. The Nuclear Regulatory Commission, that if the cost-benefit ratio is less than $1,000 per reduction of the dose or the harm that you can cause people from radiation, by one person receiving one RAM, oh, you go and implement that safety feature. We call it, in that case, it is cost beneficial, all right? Cost beneficial in that case. So that's a criteria that is given to us by the regulatory agencies, which determine the laws of the land. And if we are safety engineers, we are public servants, we have to abide by those laws, in addition to the laws of the professional societies that we cover that in the chapter on ethics in general. Notice here that in the denominator, we had, before the application of the safety feature, N type options of things going wrong or sequences of accidents. And when we apply the safety feature, we get M. And the interesting thing is that M here, because now we added complexity to the system, M can be larger than that small n. And in fact, that's what happens in the reactor safety study. To calculate the denominator and the numerator, you'll find that if we don't have an emergency safety feature, ESF is an acronym for emergency safety feature, you can have 1, 2, 3, 4 different accidents. When you add the emergency core cooling system, you still have 1, 2, 3, 4 here, the same 4 accidents, but now we have added another whole set of different accidents. However, you find that the frequency of those accidents or sequence of accidents before adding the safety feature here is very large, 10 to the minus 4. When you add the safety feature, you'll find that the frequency is reduced to 10 to the minus 6, 10 to the minus 4, and 10 to the minus 3. They change in that case. And initially, the risk from those accidents from the radiological consequence, which is man, the number of people affected multiplied into the TREM, the dose of radiation that can cause them harm, you'll find that instead of the risk being 8, 10 to the 7th, oh, wow, it has been reduced to 1/2 the amount. And when you add all those risks by adding the safety feature, you get 2.5 10 to the 4th, which is less than 1.5 10 to the 15th. So even though you added more different sequences to the whole system, but you have reduced the overall risk. So that is the concept of the cost-benefit analysis. If you want to look at the detail, you'll find that we have here an alpha and a beta. RSS stands for the reactor safety study, consequence sequence. Alpha, beta, and gamma are really the levels by which the containment that surrounds the nuclear power plants is breached by the release of radioactivity. So if you get a vessel steam explosion that's suspected in the Chernobyl accident, the core melted, it became a liquid metal, it dropped over water that was not well designed, left under the core, and in that case you get a steam explosion. And steam explosions have been common in the steel industry when they drop, say, ingots of steel to quench them into water. Sometimes the interaction between the molten steel and the water can be violent. And it happened here in our chemical engineering department. The professor was demonstrating this concept of a steam explosion by having a bucket in the front, and he poured molten lead in it. And basically steam explosion happened. And that experiment is never repeated because the steam basically affected the students standing in the first row. These ideas of steam explosions then do happen in nuclear accidents, and that is the failure mode. It can lead to the failure of the containment structure. We call it the alpha mode. The beta mode is simply one of the penetrations starts leaking the atmosphere of the containment. So in that case, radioactivity leaks with the steam under pressure, and that happens at, say, conduits that you have for the cable for the instrumentations, and as well as cable, in that case, piping that brings in the feed water heater to the steam generator, and the piping that carries the steam out from the reactor to the steam turbine. The gamma is an overpressure due to hydrogen burning. you notice if you watch the sequence of the Fukushima accident that they had a design flaw in the containment where hydrogen started getting released into the containment that they couldn't basically release it to the environment because of the design of the springs of the valves that would release the pressure of the hydrogen. And in many of the 4 reactors where the accident occurs, they had hydrogen explosions. One of them had that steam explosion. Apparently, it was extremely violent. Epsilon is a failure of the containment if the core that has melted down would interact with the concrete. And you know that to cure concrete, we add lots of water, and then you have calcium carbonate in the concrete. So the metal interacts with the water in the concrete, and then, of course, the metal can melt through the concrete into the ground. Notice here that in the accident that we considered here, it was only the alpha mode. So actually the alpha here, A, S1, S2, and TMLB become beta mode. So in that case, the containment has a less serious accident in that case. If you think about what is a T1, A, B, and L1, if you find your way designing a nuclear reactor, this is terminology for the different sequence accidents that can happen in a nuclear reactor. T1 would be the loss of offsite power. T2 would be the loss of power conversion system transient, other than the loss of offsite power. In the accident at Fukushima, when we will study it in detail, it turned out that the earthquake damaged a switching station, a transformer station, 8 kilometers from the plant. In fact, you can have fun following the lines that are coming from that station 8 kilometers away from the station by using the Google Maps. And because of the damage of the off-site transients, and nuclear power plants have usually 1 to 2 connections to the grid, so that if they lose power at the plant itself, you can get power from the grid to run your control systems and your safety equipment. That didn't happen at Fukushima because the earthquake damaged the off-site power generation. If you read the media, in the Ukraine, they have that power station there where the transmission lines have been affected by artillery kind of bombing. So in that case, they really had to shut down the plant, but they're restarting it back again. S1 in the sequence of accident would be an intermediate loss of coolant accident, and that LOCA here idea would come back to us quite a bit because the 3 Mile Island was a small break LOCA. LOCA is the acronym for loss of coolant accident. We have large LOCAs where large piping, for instance, the pipe at the Clinton plant. I used to take our class to visit the Clinton plant when they were constructing it. The pipe that carries the steam from the reactor to the turbine is 1 meter in diameter. It's that big, that size. Imagine that. So in that case, this would be a large scale loss of coolant accident. But if, say, a valve gets stuck and steam is released from a pipe diameter that's between 4 and 10 inches, we call that a small break loss of coolant accident. And there is even a small break for diameters of pipes less than 4 inches. In the 3 Mile Island accident, if we study it in more detail later, you'll find that it was a valve that got stuck in the open position of the stem. So let me show you how valves are designed for you to get the idea. If you have any container, let's say it's a steel container, pressure vessel, this is the boundary. What you use as a valve is some kind of a little triangle like this, that when you raise it, you allow the flow to move in this direction or this direction. When you lower it, you stop the flow. Now, how do you raise it up or down? Usually it's a solenoid where you run some electrical power, and it's a linear, basically, induction motor. So you raise that stem in this position, then the steam can flow. You lower it, you close the flow of water or steam. This is called the stem itself. In the 3 Mile Island accident, that valve stem opened up and did not reseat itself, even though there was a light here at the operator stand that told him, oh, well, it's lighted, so this means that that stem is operational, but it was not operational. So in that case, it was a small break loss of coolant accident for the 3 Mile Island accident in general. All right, so that identifies for us those beginning numbers here, the AS1 and T. T stands for transient. But when we go to a more elaborate or more complicated sequence of an accident like that TMLB, there is also there a terminology shown in this diagram. If you study the 3 Mile Island, for instance, the L is the emergency feed water system failure with recovery of power conversion. M is the power conversion system failure. So in that case, you could see that, this MLB, after the transient occurring, we mentioned that in conjunction with the space shuttle accident, that could be a combination of human errors, equipment failures, or design flaws other than the force cause of accidents in general that can happen to our industrial facilities, which could be natural disasters, equipment failures, human error, or design flaws. And we have to live with all these causes when we analyze accidents and design our equipment in general. Well, in that case, we said that, or we studied the use of an emergency core cooling system, and we suggested that its cost-benefit ratio is $14 per person RAM per year. That is the cost-benefit ratio. It is beneficial in cost. But there are other options that we can use in. That's Alexa, it keeps coming back. I cannot remove it from the phone. In any case, there are other options. So in that case, in an actual design of any engineering system, we consider basically a matrix of the possible additions to the safety system. And you'll find that the order in which you add the different safety features affects the overall risk and affects, in that case, the cost-benefit ratio. For instance, in our example of the seat belts and the anti-lock brakes, and then the backward camera. What if you add the anti-lock brakes before you add the belts, the seat belts? All right, you'll find that the risk is affected in that case. So here, what they do in practice is generate a matrix where you add different options in different ways. And if you have 3 different options, the emergency core cooling system that we considered earlier, adding diesel generators, that's DG stands for diesel generators, and or adding a containment to surround the whole structure. We considered that case here where the emergency core cooling system is added first, and you could see that the cost-benefit ratio is in the range of, let's say, 1.1. This is 10 to the 5th, so it's 1.1 million. Sorry, that if you take it 10, that's 10 to the 5 or 10 to the 6. I think that's 10 to the, the risk reduction is 1.1, 10 to the 5th, but the cost-benefit ratio, as we calculated it, was 14 and 14. Now, what if you add the containment first, then you add the emergency core cooling system, then you add the diesel generator? You'll find that the cost-benefit ratio of adding the containment structure is 25. Well, all right, but then adding the emergency core cooling system is not needed in that case because it is more than the $1,000 per risk reduction per RAM or man RAM in that case. Notice that you can start with the diesel generators. The cost-benefit ratio is 83. You follow it by the emergency core cooling system, it's 14. So you add those two. In that case, adding the containment is not cost beneficial, right? It costs you more than the $1,000 that the NRC is recommended for us. So if you have three different risk reduction components, you find that basically adding them depends on the order in which you adopt each one of them. And in current power plants, that's what really is adopted right now. We add the emergency core cooling system, cost-benefit ratio 14. You add the diesel generators, cost-benefit ratio 85. So in fact, you don't need the containment according to the criteria by the Nuclear Regulatory Commission. So I'm trying to show you here the detail that come in these types of calculations, considering the economic system in general. Now let's look at, in society in general, what are the cost-benefit ratios for different implementations of risk aversion or we should call them risk mitigation efforts. First, you try for the undesirable event or the risky event not to happen. You don't want the airplanes to fall off the skies or nuclear accidents to happen all the time in nuclear power plants. But if they happen, you also want, of course, the consequence to be minimized. So let's compare the cost-benefit ratio, and the unit in that case would be in millions of dollars per life saved. Notice here that the cost-benefit ratio is not dollars per year or the annualized cost. It depends on what application you are using. So in that case, there are safety implementations in society that we use. For instance, you can add kidney dialysis treatment units. You'll find that its cost-benefit ratio is $0.2 million per life saved. Or you can have mobile cardiac emergency treatment units, that's $0.03 million per life saved, which would be $30,000 per life saved. You can add cancer screening programs, and you find that it can cost you from $0.01 to $0.08 million per life saved. Fire protection, the Consumer Product Safety Commission rules on when you manufacture any kind of furniture, you have to design it to be non-flammable, so it does not catch fire. Why is this? People like to go and sleep with a cigarette in their hand, and then the cigarette falls on their furniture, on their mattress or their bed, and oops, it catches fire and the whole house goes on fire. You'll find that furniture in the United States has to be made out of, in that case, non-flammable materials. The cost-benefit ratio is 0.5. Smoke detectors is only $50,000 to $80,000 per life saved. So that's why everybody in their homes right now, we do have, all of us somehow, smoke detectors, because you could see it's very cheap to save a life. Not for an individual, $50,000 to $80,000. That's a cost to all of society. So for all of society, we save a life with a cost-benefit ratio of 50,000. I can translate this into dollars from millions of dollars, $50,000 to $80,000. Let's look at other implementation for reducing the risk and increasing safety in automotive and highway safety. Highway safety programs, that's 0.14 or $140,000 per life saved. Safety improvements since the 1970s, 32. Notice seat belt is the lowest of them. See how seat belts can save quite a bit of lives at the lowest cost. Environmental Protection Agency vinyl chloride regulation. Vinyl chloride can cause cancers, and at some point the bottles that were used for Coke, and when you buy Coke, for instance, or water, that vinyl chloride basically ends up in our bodies and can cause some cancers. In fact, the cost-benefit ratio is $4 million per life saved. The drinking water regulations is $2.5 million per life saved. Then other criteria in occupational health and safety are also part of society in terms of reducing the risk to the overall society. The coke fumes, that is happens when power plants burn coal, or the steel industry burns coal to manufacture, in that case, steel, or for producing power. That is 4.5. Benzene regulations, it's when you go to the pump at some point, or well-designed pump at the gas station, of course, absorbs the fumes that are leaking from the hose itself. That is very costly, $300 million per life saved. In the use of coal to produce power, coal coming out of our, in the Midwest here, contains a large amount of sulfur, and that's why we import our coal all the way from areas of Wyoming out west. You find that a power plant of 1,000 megawatt electric coal power plant needs every day a train of 100 cars filled with coal. In that case, you find that it comes with, if you use coal from, say, Illinois, we do have coal in Illinois, just drive to the Kennecott Cove Park out west of here in Indiana, you'll find that you equip the coal power stations with scrubbers that remove the sulfur dioxide. Why sulfur dioxide in the coal? Because in the air, if you release sulfur dioxide as a gas, it combines with water moisture in the air and turns into sulfuric acid. Then it ends up in our lungs, and of course it can cause lung disease. That's $0.1 to $1.4 million per life saved. Nuclear power plants, emergency core cooling system, the one that we studied in more detail, that's $100,000 per life saved. Radioactive waste effluent treatment plant would cost $10 million per life saved. The containment system, $4 million per life saved. The diesel generators, DZ sets, $1 million per life saved. Hydrogen recombiner, larger than $3,000 per life saved. In fact, it tells us that they're not needed at all because they're not cost beneficial. Society better spend its resources in reducing the risk in the option that has, of course, cost us the least. And you could see that has to do with cancer screening programs. You can save lots of lives. Smoke detector costs us much less. So this is where, by comparing the cost-benefit ratio for different options in providing safety and reducing the risk in society in general, it is not just nuclear power plants or coal power plants. It's the different activities that we have in society. And that's where we can say we need government, yes, for the common defense, that's sure, but also the common safety and the common well-being, the health of all of society. So if you have money in society, you better spend it on the cost-benefit ratio that is least in terms of what activities you provide. It is wasteful of resources to go and just add hydrogen recombiners to nuclear power plants when an emergency core cooling system will cost you not $3,000 million per life saved, it will cost you only $100,000 per life saved. So comparing those cost-benefit ratios allows us to make decisions on what are the better options in terms of reduction of risk. And that was more detailed about the straight approach to assessing risk, in that by adding safety features, we can reduce the risk incrementally, but as the amount that we spend becomes large, the risk reduction is very small. If you want to be more sophisticated, then you consider the overall system. That's the approach. It's not followed by in the United States, by the way. The approach of the overall system is followed in Germany. So maybe some of you may adopt it for applications in the United States. The reason or some data that were developed along this line of considering the overall economical system, it has an advantage. It tells us, okay, here is a minimum beyond which you don't want to add more safety features, because in that case, you are adding to the risk. So in that case, you have to go and study the overall economic system, and you find yourself getting data, for instance, on how much is the risk of that the workers that are building those extra safety features, the diesel generators or the anti-lock brakes or the video cameras in a car or the airbags in the car, are incurring. And you can get the data by looking at the occupational risk of producing safety equipment worth $1 million. To produce safety equipment worth $1 million, the economists suggested that you spend 87,000 hours, but over those 87,000 hours, the statistics show us that you can basically lose some working days, and the lost working days end up, of course, costing you $56 million to produce that $1 million. You can get occupational accidental death. For instance, if you are mining coal, coal accidents where people die buried in coal mines, or losing the oxygen in the coal mine. You hear about this happening in many, not in the United States as much as maybe South American companies. In China, they do happen too. In that case, that is 7.8 10 to the minus 3. That is the risk of, and then people drive to their work location. Oh, accidents happen when they're driving to their work location. And they have a difference between occupational accidental death and occupational chronic death. By chronic death, they mean death by disease. The disease that miners are subject to is black lung disease. As they mine the coal, they get the dust of coal into their lungs, and eventually the lung becomes black. But of course, they die eventually of lung disease. The accidental death would be in the coal mining industry, for instance. That would be a mine collapse and burying the hapless miners in the mines. That's another reason why, not just because of air pollution, but also because of those accidents that happen to the miners of coal, that we should basically some kind of eliminate coal from our energy picture. You calculate the total deaths, the driving fatalities, occupational chronic deaths, and the accidental deaths, and this is what you get in the cost or the risk of producing $1 million of safety equipment. So if you take the total deaths as 12.10 to minus 3 as risk, the equivalent lost persons per day is 73 person multiplied into days. And the total equivalent lost persons per day is 129 or 130 persons day lost. So that would be that R sub P here, okay, would be the slope of that curve when we consider the overall system in terms of this would be the slope of that curve. So as you are adding more safety equipment, you are using extra man hours to produce the equipment. And in that case, at some point, it doesn't pay, or it is not cost beneficial to add more safety equipment rather than just keeping and adding the numbers in the previous curve here, and according to criteria that are set to you by law by the regulatory agencies. So this is two different approaches. Obviously, it's much more elaborate, much more difficult to adopt the overall economic system approach, but it is being used, and people have been using them. More detail about the cost of risk reduction in terms of the working hours by considering the overall economic system. This shows us the working hours, the occupational accidental deaths, the job-related driving fatalities that I mentioned to you, and the occupational chronic deaths. Occupational chronic deaths is disease. Oh, in the mining of uranium, I forgot to mention that the miners are inhaling the radon gas. The radon gas is a decay product. When the uranium-238 and uranium-235 decay at room temperature, you'll find one of the products of the radiation decay is radon-222. And radon-222 have a very low boiling point. So at room temperature, it is a gas. And it is being released there out in the fields, anywhere we go, actually from bricks, if we have bricks in the ceiling, or from the calcium sulfate gypsum in materials, or in rocks or vinyl or whatever. And of course, it affects us when the radon gas itself is not toxic. What is toxic is two of the products of the decay of the radon gas, and that is polonium-210 and lead-210. They are very powerful alpha emitters. They deposit themselves in our lung tissue, in the alveoli in the lung. They start emitting alpha particles and cause now toxicity from radiation. In fact, if you go to the site of the Surgeon General, he warns us about the risk from radon-220 from uranium and radon-222 from thorium. And when you buy your new home, when you get your new job, the first thing you do is take a sample from your the basement of the home that you are going to buy before buying it, and run a test on the presence of radon. There are some remedies. You put, say, plastic, and if you have a basement on the ground, or you aerate the building better. But radon-222 is a disease-causing chronic, causing what they like to call chronic deaths in the mining of uranium, whereas black lung disease is the chronic deaths in the coal industry. So if you consider the machine tools and electrical equipment, you find that the lost working hours is 416, mining is 1,040, stone and earth also in the construction business, textile business, service provisions, construction, 630. So you could see here which one of those businesses is the more kind of risky in terms of total working hours lost. Definitely mining is a very dangerous business, and in terms of the risk that the miners face in the mining process. I've dealt with that table already, but then I showed you the detail. So here we have learned about two different approaches for estimating risk. Now, these are not the only two approaches. There are two very important approaches that we need to cover next. One is what we call fault tree analysis, and another one that we are going to call event tree analysis. Now, these two approaches that we covered now are very simple mathematically. Well, determining the indices approach is simple, taking log of 10 mathematics. This one is also a simple approach. Now, the fault tree analysis and the event tree analysis, in that case, need a mathematical background, a theory background, and that would be learning about what is a Boolean algebra, because that's the basis of the field of probability theory, and we are going to use the algebra of logic, and the algebra of logic depends on probability theory, and the De Morgan algebra is another basic mathematical construction that allows us to deal with possibilities rather than probabilities. The material that I put on the board here, I forgot here, I put it here in the appendix, so please, you can refer to it. And we stop at that for today. Thank you for your attention. Yeah, we'll stop the recording. This morning I tried